Alright, hello, my name is Conan Poppy. I'm going to be giving a class on the KiCad program right now. This is going to be a very basic intro to KiCad. So all we're going to be doing is making a simple LED flashing circuit using a 555 timer. And I actually have some very basic schematics of what that's going to look like when we're done with it. And if you wanted to model it on a breadboard, you could use this picture right here down at the bottom. But we're just going to make this in KiCad. We're going to design the entire PCB that you would print if you wanted to actually build this thing out. And I'll show you how to set it up so that you could actually have this printed at SDSU for free. Mark Bruno is he's the technician at the labs at SDSU, so he can print these on his own mill there in their facilities. So the first thing that you're going to want to do is start a new project. I already have one going right here, but to start a new one, all you would do is click on this Create New Project up in the left-hand corner, and you would name it, I've already named mine Workshop, so that's where we are. And you start with your schematic layout editor. And that opens up this as soon as you click it. And this is where you're going to build your schematic. Now this schematic isn't going to necessarily match your PCB exactly. It's more so that you know what the circuit looks like when you go on to troubleshoot, or if you have to explain it to somebody else or something like that. So in here is where you're going to actually lay out all of your components in the first place and make sure that your circuit will simulate correctly and everything like that. So in order to start laying down components, you go over to your right hand bar here and you'll have this place symbol, and you'll click on that, and then you can just start clicking, and it'll have to load your libraries for a while. Every time you start a new project, it reloads the libraries, so you just have to wait for that to happen. Now, if we open up our picture again, we see that we're going to need 2 resistors, a potentiometer, a 555 timer, an LED, and a capacitor. We'll also need a 9-volt battery, but you don't have to place that on your diagram. You just need power in and ground. So let's start placing some components down. We'll start with the resistors. So we're going to have to go to this filter. And if you know where the resistors are, you can just scroll down to it. They're in devices, but in case you didn't know that they're in devices, because that's not necessarily intuitive, you can also just type resistor. And then you just scroll down a little bit. So here, R, we have resistors. Okay. So we know we're going to need 2 of those. So let's just put 2 of them down. And then we also know that we're going to need a capacitor, so the same thing, you can just type in cap. So we're actually going to want a polarized capacitor. So let's find one of those. Polarized capacitor. Alright, here we go. I like the way this one looks. You could also use this, but we're going to go with this. Mostly so that it matches our diagram here that we're trying to rebuild. Let's put down our potentiometer, same thing, you're just going to search for it. Potentiometer, RPOT, okay. Let's throw that one down. And it really doesn't matter where you put these on your schematic as you're going, because you're just going to end up moving things around anyway. Now the 555 timer is a little tricky because if you're going to build this at SDSU, they have a whole bunch of 555 timers that you can just take, but it's very specific which ones they have. Like these LMs, SDSU doesn't have those, you would have to order them. What SDSU does have is these NA and NE 555 timers. And what I like to use is this one right here, because these ones that say like SOIC, these are all surface mount, and while you can do that, it's going to be more difficult for you to put together when you when you actually sit down to solder this thing at SDSU. They have both the surface mount and the through holes, but through hole is just simpler, so I like to use that one. Slap that guy down. Now what else do we still need? We still need our LED, and then we'll need a way to hook our power up. So I'll show you how to do that too. So let's get an LED out. Alright, here we'll just go with the most basic one. We'll slap that guy down. And now for the power, we need connectors. Now there's all kinds of connectors that you can choose from. Generic, you're going to want just like a 1x1 because you're just going to end up soldering some leads from a battery terminal onto it. But let's not use this particular symbol, mostly because I don't like the way it looks. We'll go with this generic one right here. If you press R while holding it, it'll rotate it so that you can actually get them facing the direction you want. And then if you want to zoom in and out on your scroll wheel, it'll automatically just go to wherever you're centered. So you can see all the automatically generated information about your design, or you can just zoom in on your parts if you want, just in case you wanted to move around. Okay, now let's start actually hooking all of this stuff up. Actually, there's one more thing we're going to need. So since you are designing an actual PCB here, you're going to need mounting holes, which are not something that you would normally have on a schematic diagram like you would see in your EE210 book, but you do need them here. And they're actually super useful because they will they'll act as a ground later when we actually design the PCB. So we're going to need 4 of those. Oh, and you can use Control-C and Control-V just like any other program to copy and paste whatever you're doing. Now you see how they all have like C question mark, R question mark? That's because none of these are labeled and none of them have values yet. So we want to start giving them just common names. So we'll call the diode diode 1. Our timer is U1. We'll just go through and name all of these. Now, one of our resistors needs to be 3.3K and the other one needs to be 10K. So we'll call this R2 and we'll say that that's 3.3K. We'll call this R1 and say that it's 10K. Our trim pot is going to be RV3, or sorry, RV1, and its value needs to be 100K. Variable, so it'll go from 0 to 100K. Let's see, our capacitor needed to be 10 microfarads. So we'll change that. Call it C1. And the circuit's not actually going to simulate these values. These are mostly just for you so that when you go back to look at your circuit, you know what those resistors values were supposed to be. This isn't like Spice where it's actually going to simulate that resistance. It's just names. Alright, so let's name our mounting holes and everything like that too. Mounting hole 1. These don't actually matter, it's just good practice to name everything, because once circuits get more complicated, it's nice to know what you're looking at. And since this program is capable of doing more than one PCB at a time, it's entirely possible to have your mounting holes on the wrong board if you're simulating or designing more than one board at a time. So now it's time to get this thing basically looking like how it looks in this picture. Now it's not going to look exactly the same, mostly because, as you can see, our pins aren't in the same place. Like our ground pin is in the same place, and 8 is in the same place. 3 is kind of in the same spot, but see, 6 and 7 are on completely opposite sides. 5 isn't even accounted for. 4 is up here on the top instead. So our circuit's going to end up looking kind of different from this, but we can at least put the components in the same-ish spots. So they have that up there. They have their 3K up here. Have their 10K. Capacitor going to ground. And our potentiometer is here. So we'll do it kind of like that. Let's move these out of the way a bit just so that we don't have to worry about them. Actually, we'll put them up here. I accidentally named these both J1, so that's an issue. There we go. Now, one of these is just going to go to ground, and the other one is going to be our power rail. So if we want to, we can start setting up the ground right now. And we can say, to go over here onto the right, we can place a wire, and we can just have it go straight out from here if we wanted. And then we could connect that directly to this one here, or what we can do, that's not what I wanted, we can place our ground flag So we come in here and we start looking around, and we see that way down in here we have just a very basic ground signal, or ground symbol, I mean. So slap one of those down. There we go. So now we're saying that we have this goes to ground. Alright, cool. Now if we put another ground flag at the bottom of 1, we can start using this as a bar to say that, okay, so now the capacitor also goes to ground. What else did we have connected to ground? So the other side of the battery, obviously. Okay, so nothing else is connected directly to ground. But now we have a lot of things that are connected to this side of our capacitor, the positive side. So we have pin 2 and pin 6 are both connected to the positive side of the capacitor. So let's start drawing those. Pin 6 goes to the positive side. Pin 2 goes to the positive side. Okay. Now we have power goes into pin 8, pin 4, and the top of our diode. So we can do this. We can say power goes into the top of the diode, goes into pin 8, and goes to pin 4. Let's try to... yeah, we can go this way. What else are we missing here? Okay. Oops. All right. Now, pin 8 also goes to the top of our potentiometer here. Now pin 3 on this potentiometer is going to go to ground. So if we want to, we can just put another ground flag there, which I will do just because our lines are already getting messy, and I can tell that that'll be a confusing problem in the future. And then we'll just back this guy up a little bit. Connect pin 3 to ground, connect pin 1 to the power. And then pin 2, which is where the sweeper arm is going to be connected to pin 7. So bring that all the way around here and put it into pin 7. Okay. Now we just need to figure out where pin 3 goes and what pin 5 is doing. We could also connect these. Now, I already know that pin 3 is our output. That's what Q means here. So we know that whatever this timer is doing, the signal that it supplies needs to go into the resistor to apply current to control into the LED. Let's make sure that I'm right. Okay, pin 3 just goes in. Now, what's important is that even though this isn't simulating anything and these values don't actually mean anything to the program, it does need to know where power is entering into the circuit, because it doesn't know that these connectors are for a battery. So you have to give it a power flag. So you go over here and you type in just power. Okay, power flags. Now what power flags do is they tell the program that power is being applied to the circuit. So you just put one there. It doesn't actually matter, as long as you have it on the same net as your input, it'll be able to figure that out. Now there is one more thing that we have to do, and that's these mounting holes need to be taken care of. We need to actually tell the program that these are going to be a ground. So we'll add one more ground in. We'll take this and we'll give it a rail. Then we'll connect all of these to the rail. Okay, so these are all connected to ground now. But it also needs to know that these are that this ground has a power flag, because the power does eventually need to also go to ground. If it's not grounded, then it's not doing anything. So we need a power flag on this side too. We can just put that right there. So, oh, I have forgotten this resistor here. How is that supposed to be set up? Okay, so 10K goes from this pin into the 10K and into ground. All right, that's pretty simple. So this is making a voltage divider into ground. So what this means is that no matter what, you'll always have at least 10K of resistance going into the timer. So it will always have at least a minimum of a 10K feedback. And then you can bring that all the way up to 110K. All right. So we think that we have our circuit completely laid out now. It matches this guy pretty well. So what you'll want to do is run your debugger. Now I know that there's at least one problem on here, so hopefully the debugger will only find that one. Alright, good. So it only found that pin 5 is an input and it has no connection. And it's suggesting that we use a no connection flag to suppress that error, which is a perfect idea because pin 5 doesn't actually do anything. And you can see it even gave us a little arrow saying, hey, here's your problem. So if we go over here on the right and we just say place no connection flag and click Control Z and click at the end of 5, then we're telling the program that we know that there's no connection there, and that's fine. So now if we run the debugger again, it'll just say no errors. So this whole circuit is technically done now. So let's generate our netlist. So this changes for the program. It's not actually going to change our schematic, but it's the program side is going to see these all as just compressed nets. It only cares about which nodes do what and how they're attached together. Because when we actually throw this into the PCB designer, it's not going to look like this at all. It's just going to have our components, and it's just going to tell us what is connected to what in order to make the circuit work. So we'll generate that netlist. It'll ask us where it wants us to save. I want to keep everything in my workshop. Perfect. Now we do one more step before we're actually ready to design this, and this is actually probably the trickiest step, and that's assigning footprints to all of these components. So you'll come up here to the top, right next to our debugger, and we'll say assign PCB footprints to the schematic symbols. Now it's going to have to load all of our footprint libraries back up, but it's also going to tell us everything in the schematic that needs a footprint assigned to it. That way, when we actually go to design the PCB, it can give us the courtyards, and it'll tell us how big everything is going to be and how much space it needs, how much copper it needs, and basically what the mill needs to do to produce this PCB for us. So we'll just wait forever for that to load. All right, so these are all of our components. You can see that they don't have footprints except for the 555 timer. This one, the footprint can't be changed, so it's automatic. It tells you exactly what you're going to need to make that 555 timer work. But everything else, the capacitor, the LED, the mounting holes, it doesn't know what those footprints look like, so it's asking us to tell it. So we'll start at the top. We'll go to this capacitor. And you'll go over here to your footprint libraries on the left-hand side. And you'll see, okay, I'm looking for capacitor. These are all connectors. Okay. So, oh, here's capacitor. Now, SMD, that's going to be a surface mount. We don't want to do that just because they're more difficult and harder to find in SDSU. We want through hole. That's THT right here. So THT, now these over here are all your different sizes of through-hole capacitors. Now, when you're deciding on what size you want, you really need to know how big you want your circuit board to be. You want to know how spread out you want your leads. You want to know how big those leads are. Basically, you just need to know. You need a pair of calipers, really, to figure out exactly how big everything is going to be. Or you can just assume that you're going to be using regular capacitors and you'll fit the board around your components instead of trying to fit components to your board. So I already know that we want a radial capacitor, so none of these axials. Okay, so here's radial, and we want 8mm and we want 2.5mm. And if you don't know what any of these things look like, you can come up here to the top left and you can say View Selected Footprint. And this will tell you, this will show you what it's going to look like. So you have your positive side, you have your ground side, and these yellow pads are actually the copper that you'll see when you go to solder this onto the board. So this looks pretty good. We can stuff pretty much any capacitor into this. These holes in the center are for the leads of the capacitor, so this is fine. This will work for us. So you'll select it, you'll double click, and now it's assigned the capacitor footprint to that capacitor. Now we'll do the same thing with the LED. We'll come through here. We'll say, okay, we don't want any of these. Here's a through-hole LED. That's what we want. Now what size through-hole LED do we want? So we know that 8mm worked for the capacitor, so let's just use another 8mm for our LED. Scroll down until we start seeing 8mm. We'll use this one. Alright. And if we want to, we can look at what that looked like. Pretty much exactly like the capacitor's layout, except it has a different silk screen. And I'll explain silk screen when we get to the PCB. But this is just telling you that it's an LED, not a capacitor. Mounting holes. Okay, same thing again. Mounting hole. Alright, this works. How big do we want that mounting hole to be? Let's call it 6mm instead of 8. And the reason I'm choosing 6mm is actually just because that's what some of the senior design lab instructors will want is because 6mm mounting holes will fit a number 6 screw, and a lot of them have that specification. I'm not sure exactly why. I think it's just to make our lives more difficult, or maybe even more simple, who knows, but use the 6mm because that'll fit a number 6 screw. So we'll apply that to all of our mounting holes. Now all of our mounting holes are the same size. Now for the connector, and I'll just hurry this up a little bit. Connector. Through-hole connector, cool. And I just took a note that we want size 271 way down here. Oh, that's not a connector. Where's my connectors at? Connector pin header. We'll just use these. That'll work. Actually, no. I don't want to use those. I'm going to open up a different program real quick to see which connectors I've used before. So for these ones, I used a connector solder wire. Okay. Connector, wire, solder wire, and I used, in this one I used 271. Here we go. Scroll all the way down. Now these are useful because instead of telling somebody that they're looking for like a 2 square millimeter, 1x1, 2mm, whatever, all of this, you can just say go to 271 in this list. So there we go, another 271. Alright, now for the resistors. Through-hole resistor, number 20. Now these ones, it doesn't matter because all resistors are going to be the same size essentially, so we can just use the same resistor for this one as well. Now this pot is very specific to what SDSU happens to have a supply of in their lab. So let's look at our through-hole potentiometers. Now you may want to just keep this in mind. SDSU only stocks one kind of potentiometer footprint, and that's this one right here, this Burns 3339P vertical. Now hand soldering just means that the pads are going to be bigger and easier for you to use, so that's definitely what you would want. If you pick a different footprint, SDSU is not going to have those potentiometers, so you'll have to order your own, which is perfectly fine, but if you want this to be completely free, just use this one because that's what SDSU has. Okay, we now have all of our footprints assigned, so we'll apply, we'll save the schematic, and we'll continue. We'll click it again just for good measure, we'll say OK. Now let's make sure they all stayed, because we don't want to go through all of that mess again. Alright, good, they're all still there. Now, we'll generate the net list again. Nothing should change, but we'll just update it just in case. And now we get to do the fun part. If you go to this right here, the Run PCB to Layout Printed Circuit Board, this is going to take us into the actual editor for the PCB, which is the whole point of this. This is the exciting part. Now this is where we're going to actually design what our board looks like. But you can see we don't have any components. Now you might be thinking we have to reset all the components again, which would be super annoying. You actually don't. If you come up to the top, right next to this debugger, you have Update PCB from Schematic. Click that, and it's going to tell you all of this information. It's going to say, hey, these are what we see on your schematic, and this is what we can put on your PCB. And it's asking you if you want to keep your existing symbol footprints or not, and obviously we do. We just spent all that time figuring out with calipers how big everything needs to be, so we'll just keep them. And we'll update the PCB, and you can see it just spat everything out up at the top. And it just makes it as small as possible. And now we're holding all of our components, and this is what I meant by it's not going to look like the schematic, because all that the program cares about is the nets. What's connected to what, which node goes where. So we have to make this look nice. I mean, of course, we could just print this out, but nobody wants to try to solder all of this. If you tried to make all of your traces work, like, it's just going to be a mess. It won't be very fun. So let's start moving things around, kind of make it look like how we want. So we'll select pad 1, move that over there. Mounting hole 2. We'll move mounting hole 2 over here. Mounting hole 3. Move that guy over there. Mounting hole 4. Now, this is telling you where your centers are, these lines, so you can try to get everything sort of lined up. Here we go. This is our ground pin for our battery, so we'll want that at the top somewhere, maybe on the side actually, so we can just have our battery chilling on the side, and we'll plug everything in. Okay. Now we remember our diode was up here somewhere. We had resistor 2 going directly into the diode. Now these white lines are telling you which nodes are connected to what. They don't actually, they're not physically there. You'll have to put the traces in yourself later. Again, R makes things rotate, in case you're confused by why all of my components are flipping around as I'm doing this. But you can kind of see, like, with all your white lines, it's a pretty good idea of how difficult things are going to be to connect up. Because if you have a bunch of white lines crossing each other, like this would not be fun to connect. That's a little better, that's okay, that's probably the best for connecting. This cap down here needs to move. We'll put it that looks all right for connecting. Okay, so we've got a basic idea of how we want our printed circuit board to be laid out. So now it's time to actually start laying down copper and telling the mill what needs to be done so that we can solder on this thing. So Mark Bruno has a whole bunch of rules and things. I can open those up real quick. I'm not going to go through all of them right now just because he has a lot, and I'll make this available on our Discord and things like that. But you can see he's got rules for how far traces can be apart, how far holes can be from traces to the edge of the board, basic sizes for typical traces, things like that. It's all pretty important. He won't print it out if you don't follow his guidelines. So before you print, just email him, or before you actually send him your Gerber files, just make sure that you're following his guidelines. And if you don't know what they are, you can ask him, or you can ask anyone in IEEE. We can get those guidelines for you. but you will want to, first off, make sure that all those guidelines are already set for you so you don't have to worry about them later. Come up here to the top left where it says Board Setup, give that a click, and you'll want to go to Net Classes. Now, your default net right here, see all of these nets are already default. So he had his clearance at 0.7 millimeters. He had his track width at also 0.7. Sorry, he had the clearance at 0.9. Track width was 0.7 millimeter. Via size. Now, vias are actual physical holes that get put into the board to make sure that the copper can spread from one side to the other. So those are actually really important. And he has his via size as 0.7 millimeters. We'll make the actual size of the via drill also 0.7 millimeters. Okay. So now this is your default now, but none of these have actually had that applied to them. So you'll say assign a net class default assigned to all listed nets right here. So that makes all of these have the same default. All right. Oh. Put this back down to 0.6. Okay. Now, before we can even start traces, there's still one more thing that we need to do, and that's we need to do our front, our back, and actually assign the size of the board. Now, to assign the size of the board, you come over here to all of your different layers, and you'll go to Edge Cuts. This tells the mill, with the Gerber files, how big to actually make our board. So we'll go to Edge Cuts, and we'll just go to this. We'll just go to Add Graphic Lines. And we'll say that we want one edge to start here, go all the way over there, come down, go all the way over there. All right. So this is actually going to be the size of our board now. What you'll also need to place down for this is a drill in place offset. This can go literally anywhere, it doesn't matter. It's just for the program to know how to tell the mill where to start and where to end. Like I said, that can go anywhere, but it absolutely has to be there or the mill won't know what it's doing. Okay. So now let's do our copper layers. So we're going to add a filled zone. Now these are the two layers you'll be working on the most, the front copper layer and the back copper layer. So we'll do the front copper fill zone first. Come out here to the edge. Now we want these to all go to ground. You always want your filled copper to go to ground. At least for SDSU's sake. If you're having it printed at SDSU, you have to make sure that your filled zones on the front and the back all go to ground. This is going to be more drawing of squares. My lines weren't straight, so I'll fix those. Okay. Okay, so that's the front copper done. Now you'll do the exact same thing on the back copper. Same thing, I want you to go to ground. Okay. Now we'll have front and back copper done. Now if you want to, you can just you could simulate this right now and get a look for how that copper is going to look. Let's see, did that actually fill in? Yeah, that did. Okay. So we see here how these are actually connected to the ground now. Like that's exactly what we want to see. Same with these. Now for some reason my mounting holes aren't connected to ground, and that's a little weird. I might have to figure that out later. But anyway, if we want to actually see what you're doing, you can turn this on, turn it off, see what's connected to ground and what's not, so that's all good. This is the view we want for now. Because now we're ready to actually start doing the traces, and our trace widths are already set up. So we'll do as much as we can on the back copper here. Not everything is going to be able to fit on the back because some of our traces are going to have to cross over, and that's when you move into the front. But we can do most of it on the back here. Now this program's cool because you can, it just like automatically loops around stuff for you. It does a pretty good job of making sure that things will fit together right. Also, it keeps things at 45-degree angles, which is super nice because 90s are, people don't really like to see 90s when you're designing these things. So we can start just throwing all of our traces together. We'll get as much as we can on the front copper. I'm not going to worry about making this super pretty right now. I'm just going to get it all put together. When you make your own boards, it's pretty important to make sure that everything looks nice, mostly for your own sake, because there's just something about making an aesthetically pleasing board. It's not always great to have everything be a mess. Now, see with this one, since I'm on the back copper right now, it's okay to go underneath the IC, mostly because the IC is not actually going to sit on top of this copper. If this was the front copper, you wouldn't want to go under the IC like this, but since we're on the back, this is okay for now. We could also bring this guy over here because those are connected. Let's see, what other connections do we have to make? So we need some way to connect this pin to this pin. Now see, the program wants me to go all the way over here. It's also saying that I could connect to this. So I guess we can bring one way up here, all the way over here. See how that's making two 90s? We don't really want that. But we can do this. Have it go there. Now we have to make this connection. So again, we could bring this all the way up here. And this last connection is going to be pretty painful, so we'll just keep this actually on the surface. So we'll get out of our back copper and we'll go to our front copper and we'll say, okay, we want this one to go up and around. Okay, so now everything is hooked up. So when we ran the debugger though, it was saying that, I'll just run it again, we'll just read the same error. Refill the zones. So it's saying that pad 2 and pad 1 of our diode are too close together, and that's because of the clearance parameters that we set earlier. The mill at SDSU is saying that it can't mill this out these close together. So what you want to do is select it, double click, and now you can go into your local clearance settings. You could also just go into these general footprints and everything like that, and we could actually edit the footprint. So we want this to be much smaller. Let's actually do it a different way. Let's just go to properties and edit it that way. There we go. So you want to change the properties of the pad, not the LED. That's a mistake I was making. So I already tinkered with this a bunch, and I know that if I make the diameter 1.2 on this pad, and I make the diameter, well, first off, I turn this one into a circle as well, so change the shape to a circle and change its diameter to 1.2 as well. Now, this gives us enough copper that we could go in there and actually solder things to it, but it's also going to make it so that they have more than enough clearance between each other that running the debugger won't give us any errors. So now it's finished. So now, technically, this is a completed board. There are still some things that you would want to add to this. A good thing to do would be to come over here on your right and go to this front silk screen and add some text so you could give yourself a name. So this is IEEE Workshop board. Call it version 1. Actually, we'll call it revision 1. All right. So now, when SDSU prints this, you won't see this this silk screen because they don't have any way to print the silk screen. But if you were to send this to some other company like JLC PCB, you would actually see that it says IEEE Workshop Board Revision 1 when you print this out. You could do the same thing and say that, hey, this is my battery input, this goes to ground. You could do all of that. Like this R2, D1, those are all going to show up on the silk screen. But you can see like LED here and mounting hole, these are on the drawings. Those won't show up. You can tell them to by just changing them onto the silk screen layer, but for now they won't. So we'll do this again just because that refills all of our stuff. Take a look at how this looks. Okay, so this is all of our front copper, all of our back copper. Now you see how this isn't getting both copper layers? To get that to pass through, you need to come over here to the right and add vias. So just add a couple in there. That's going to put a physical hole through the board so that when this gets milled, both sides get filled with the copper. Because it doesn't fill it on both sides, it needs through holes to actually get there. And now you'll see that if we run this again, now this is all filled in because our vias actually allowed the copper to flow through. Now if you want to get a look at how this thing actually turned out, you can go to your 3D viewer and it'll render for you a nice little representation of what your capacitor looks like, or what your board looks like. So you can see that we have our one trace that goes on the surface or on the front copper and all of our traces on the back, and you can see your through holes So there you go. That's what your nice little LED flasher would look like. And this is the potentiometer. You would turn this to make this flash faster or slower. Now let's say you actually wanted to get this printed at SDSU. So to actually get it printed, you've done your debugging, all of that. You figured out your diode pads. You've got everything right. This is complete. This is what you want to see. So you go to File. You'll go to Plot. And these are all the files that you're about to make. But the first one that you need to do is you need to generate your drill files. You'll just want to output those somewhere that you recognize. So within our workshop folder, we'll make a new folder and we'll call it Gerbers. Okay. So we'll put our drill into, or our drill files into Gerber. Now this Exelon right here, this is something that Mark Bruno wants specifically, so just always leave that alone. And this PostScript is just like an industry standard. PostScript has been around for ages, like years and years and years and years. Everybody uses PostScript. Just keep it. That's good for you. Generate drill file. All right. So that's done. We can close this, and now these are choosing what files you would want to send to the mill to have this thing made. So you want your front and your back copper, obviously. That's how all of your current is going to flow. We don't need the adhesive. It's defaulted to not on. The paste, we're not doing surface mount, so we don't need paste. But you might as well leave it there. It doesn't hurt anything to have it. Same with the silk screen. Mark Bruno can't print it, but it doesn't hurt to put it on there. The copper mask, that's also something that SDSU can't do, but JLC PCB definitely can, and it's super useful. So leave that on there just in case you decide to send this to a more professional fabricator than Mark Bruno's mill can do. Edge cuts, you need that so that you can know how big your board is. So these are actually all pretty much set. You don't need to turn anything on or off here. The default is fine. And then you plot it. And that's all your files done. So now if you go into your directory and you go to Workshop, go to Gerbers, these are all of the files that you would need to send to Mark Bruno to get him to print this board for you. And then you could go to his office, pick up your circuit board, walk over to the soldering station, start grabbing components, and you could just put this whole thing together. And as long as you ask him nicely, he can give you a 9-volt battery and a connector pad, and you could just put this thing together. Probably take you 15-20 minutes, and you could play with your little blinking LED if you felt like it. Or if you wanted to just prototype this at home, you could go here. And I've put both his rules and this file into the Discord, so you can look at those on your own if you want, and you can put this thing together. Hopefully we'll be allowed to go on campus soon, and I could actually, either me or Mark Bruno can show you how to solder this thing together at some point, maybe. But yeah, that's a very basic rundown, going from just an idea, just a schematic, just a little circuit diagram, and producing an actual circuit board that you could physically hold, put together, and actually operate, if you wanted to. So yeah, that's it from me. Yeah, thanks for watching.